Now it's recording. You can start.
It's not sharing yet.
Okay, so should we start or?
Yes, you can start. It's recording.
Okay.
And you, Maison, you'll let other people into the meeting if they come later.
Okay.
Is that okay?
Yeah, yes, it's okay. No problem.
Okay. Just check first. So, just share the screen. And, okay.
Okay, can you see the screen?
Yes.
Okay, so good afternoon, everyone. Today we will have our speakers from VUB, and the first one is Jean-Guillaume Feignol. So he is from the second cohort, and he did his PhD in natural science in the specialty of earth science at the University of Vienna. He did his master in earth science in the specialty of volcanology in France at the University of Blaise Pascal, and also his bachelor in earth science at the same university. He has 10 papers published in referred journals, including for first author, and he has attended regular international scientific conferences. And today he will talk about the SIF Fellows impact structure and its ejecta aggregation process. So, Jean-Guillaume, the floor is yours. You will have 10 minutes, and I will remind you 1 more minute is left.
I will try to stay in time. So can you see the screen slide? It's good?
Yes, we can see it.
Perfect. So good afternoon, everyone. Thank you for inviting me to present at the EUTOPIA Day my work here at VUB at IMGC on the Chicxulub impact structure and its ejecta, and more specifically the aggregation processes. So at first, some words about Chicxulub. So it's an impact structure or impact crater located here in Mexico, the northwestern part of the Yucatan Peninsula. And it's well known because it's this impact event that was the source of the extinction of the non-avian dinosaur and around 75% of the species around 66 million years ago. And this crater here is related to a worldwide deposit of clays, of fine dust, enriched in iridium and shock minerals, which are evidence for an impact, meteorite impact origin. And it's the third largest impact structure on Earth, and the most recent of the third largest impact structure, between 180 and 200 kilometers in diameter. And apart from the fact that it's related to the dinosaur extinction, what is interesting with the Chicxulub is also it's because the only impact structure on Earth with a well-preserved peak ring. So what's a peak ring? It's a ring of hill. Here you can see on this photograph of the Schrödinger crater on the moon. It's a ring of hills that form on the crater floor here. And there was a lot of questions about how it formed, etc. And the problem, of course, it could be a bit difficult to go on the moon, just pick samples and come back. So it was a bit more easy to study the Chicxulub in order to understand how the peak ring formed. And the only thing is that we have to drill inside because today the Chicxulub is buried under around 1 kilometer of rock of sediment. So if you go today on the Yucatan at the Chicxulub Puerto, which gives its name to the crater, you don't see anything. You just see just flat land of carbonate, and the crater is beneath the surface, so you have to drill to get some samples. And during my PhD, I worked on samples that were drilled within the crater in 2016. on the peak ring, and the study of these drill core samples here allowed to reconstruct what happened roughly at the site of the impact. So 66 million years ago, an asteroid of 10, 12 kilometers struck the surface of the Earth at 20, 30 kilometers per second, and create this transient crater here of 100 kilometers in diameter, 15 to 20 kilometers depth, excavate material. Those asteroids were fully vaporized. The basement rock were shocked, fractured, very weakened, and of course here in this red area, the energy was so intense that the rock melt here, forming that we call impact melt rock, which are like of a magma. And at the same time, material is excavated at high energy outside the crater in the form of a shock front, a blast wave with very high energy, supersonic speeds here that destroy everything around the crater, and then followed by an ejecta curtain here, rich in material from the crater, also material grabbed from the surface here. We have ballistic ejecta of a class of target rock material, also melting material. And at the same time, we have also injection at high altitude into the atmosphere of an impact plume, rich in dust, sulfur, soot, and also meteoritic material. And this impact plume traveled all around the globe, provoking an impact winter for 2 years that stopped photosynthesis processes. And all the dust, it took about 15 to 20 years to fall back at the surface. So here you see a representation of the Yucatan Peninsula before the impact, which was covered at the time of a shallow sea, because the seawater level during the Cretaceous was higher from 10, 20 meters than today. And so the asteroid struck here and wiped out all the Gulf of Mexico with tsunami, and then the ejecting material falling back at high temperature from wildfire, etc., that destroy everything around, especially in North America. So from this record, we know a bit the scenario of what happened inside the crater site, and a bit further away outside. But we have still questions remaining about this area here, so which is relatively close to the crater, from a few hundreds of kilometers away from the crater. In this area, we have the deposit of the proximal impact ejecta, which are relatively thick, but there is still question about what was the dynamic emplacement of this proximal impact ejecta, and that's come to the project here of particle aggregations, which is a project at the interface between impact cratering research and also volcanology. So at first I will define what is particle aggregation. So it's in a turbulent cloud of material rich in hot gas, dust, etc. You will have particles, very small, few millimeters or micrometers inside, that will be also in presence of a binding agent that could be either water or electrostatic forces. And these particles in the cloud will stuck together, forming an aggregate that will resist collision with other particles and will grab more and more dust and material around. And then at what point this aggregate will fall from the dust cloud here, so removing dust material from the cloud. And this aggregation process is well known to also occur during explosive volcanic eruptions. It's very well described, well documented, aggregates were classified, etc. But for meteorite impact aggregates, it's remained poorly understood. And ash aggregation is also used in volcanology to model, for example, to forecast ash cloud dispersal during an explosive volcanic eruption, because it can remove a significant amount of dust from the cloud. So here you can see example of aggregates from volcanic deposits here in Tenerife, in Canary Island, where you see these small balls from a few millimeters inside here, which are aggregates of dust that fall back inside the deposits. And during volcanic eruption, it generally forms in this kind of very big ash cloud. Here, I suppose that I took in 2010 in Montserrat, in the West Indies. We have the pyroclastic flow, which is horizontal here. And above the pyroclastic flow, we have expanded trapping and taking air from the atmosphere in water, and aggregation occur inside this kind of dust cloud here. Now, let's back to the Chicxulub ejecta. So we, as a starting point, we worked on 2 ejecta sites here that contain also this kind of aggregates that we call here accretionary class, or AC, to distinguish from the volcanic aggregates. So the first location is here on the southeastern part of the Yucatan Peninsula, the Albion Formation, which is 350 kilometers southeast from Chicxulub. And the other one, a bit further away, called El Guayal, which is 520 kilometers southwest from Chicxulub. Now, of course, to understand how this deposit is emplaced, we have to go on the field to look at how the rocks are disposed here. And if you see here a representation of the different rocks, type of rocks we can observe at Ramonal, here, the Albion Formation, so the closest to the Chicxulub. So we have on the lower part the pre-impact rocks that were there before the impact, the Cretaceous rock, which are mainly carbonate or dolomite, which is the carbonate with magnesium. Then above, we have the spheroid beds and diamantite, which are directly related to the impact. Okay. So, and in these spheroid beds, we observe there's small accretionary clast here, the surrounding pink spheroid here, mainly composed of a material which is very similar to the Barton Creek Formation. Then, going at El Guayal, we have again our stratigraphic section as a Cretaceous rock before, and then on the upper part of the deposit, we observe these beds of accretionary clast here, which are 2-3 centimeters in size here. And these ones are very similar to the aggregates we can observe in volcanoes, in volcanic eruptions, so that suggests that probably they form in a similar way. So we are able to classify these different kinds of aggregates from pore structure, the ones, the AC2, which are typical also from the volcanic aggregates with concentric structure corresponding to a movement inside the cloud, and they grab particles from different sides. And this one also with a large lithic core, millimeter size, surrounded by a fine matrix here. Here, in terms of chemistry, we have the aggregates from Mauna which are rich in calcium, mainly on iron, in this chemical map here, on the lower part representing silicium, calcium, and iron in the Polish section. At El Guayal, there is interesting difference with the aggregates rich in silica, while the matrix inside have a different composition. So that's a bit a question how we have this silica. So to wrap up, we work now on how these aggregates could form in the proximal impact ejecta. So here, probably at first, we have the passage of these shock fronts at high energy, developing a high density current, which in material from the impact, also in gas, water, etc. And probably due to this high energy on the carbonate platform, this ripped up this untrained clast here from the surface inside the current here. And then clasts were segregated here in different size, and especially during the passage of this highly concentrated, highly energetic current at the interface in between here, we will form probably by electrostatic charging of particles due to shearing, rolling, this accretionary clast composed of carbonate and dolomite at Ramonal. Then, going further away, the energy of the blast of the current decreased. More air is entrained in the flow. Also, at the time of the impact, we had some water here. So probably we have water that went inside the cloud, forming probably a pyroclastic flow-like cloud with water. So making suitable condition to form this big aggregates here with concentric lamination at El Guayal. Then, to finish, the next step will be to investigate at other large infrastructure where we have aggregate to see if we have similar processes or something totally different. Some hypotheses propose that some aggregates could come from the high altitude impact plume and then fall back on the surface, and also to see if the extent of this particular accretion in impact ejecta is something important that removes a significant amount of dust in the cloud or not. And I thank you for your attention.
Thanks, Jean-Guillaume. I don't know if there is any question.
Yes. Can you hear me?
Yes,
Yeah.
go ahead.
That was wonderful, Jean-Guillaume. Mate, can you tell us, have you done any, had any interesting experiences in your field work? Up close, these seem like particularly dangerous phenomena. I mean, obviously that was 65 million years ago, but these are dynamic structures and dynamic phenomena. Have you had course to do field work that's a bit risky?
For hopefully for fieldwork it was fine now because it's well all is well emplaced now. So in Mexico, so that's why you are that's what you are asking, right? If it was risky to do fieldwork in this area.
Oh no, generally, just generally, because there's Iceland, there's things blowing up all the time, aren't there?
Yeah. So yeah, it's a question. So for the footage I show, we were at the volcanic observatories that had a bunker, so probably we were a bit safe. But yeah, it's always we have still to be careful when this, because the problem today for especially for explosive volcanic eruption, we cannot always say what will be the power. I would say the power of the eruption. It could be more powerful than expected, and sometimes. So yeah, you have still a risk. You have to well think about it before just going to the field and.
Okay. Thank you.
Is there any more questions? I think today we will not have any breakout rooms, so please ask now or. Okay, if not, we will go to the second speaker. Just first, I'll remind you that you can fill in the form, the online form. There is a link on the chat. So the second speaker of today is Ashima Bajaj, and she's from the third cohort. She did her PhD in theoretical and computational chemistry at the Institute of Neuroscience and Technology in India. She did her master and bachelor's in physics, also in India at the Punjab University. And she was able to mix the physics and the computational chemistry. So she has a lot of interdisciplinary background. Before the EUTOPIA SIF Fellowship, she was a postdoc at the University of Buffalo. So she has more than 10 publications, and she has attended 10 international conferences with poster and oral presentation. So today she will talk about boosting automated reaction mechanism discovery using quantum chemical reactivity descriptors. So Ashima, the floor is yours.
Yeah. The animations will work from the browser. You think so? You're worried about that? So there are a bit of animations in this case. Thanks, Irene, for the kind introduction. Good afternoon, everyone. So the title of my presentation is Boosting Automated Reaction Mechanism Discovery Using Quantum Chemical Reactivity Descriptors. Putting it in the simpler words, it's about the chemical reactions and mechanisms. Where I will talk about that how the reactions takes place without actually looking into how those reactions takes place in the laboratory. And I hope by the end of my talk, I'll be able to convince you that how theoretical chemistry and computer technology, it has reached to a state where we like kind of predict the reaction mechanism without being actually able to see what's happening at that tiny microscopic level in the labs. And cherry on the top of it is like we can also predict the reaction mechanisms in a kind of automated way, where like we can minimize the human guided characterization of these pathways. Okay, to start with, since it's fairly for a general audience, I'll start with the titles are hidden, or is it okay? Okay, so since it's for a fairly general audience, I'll start with the thank you. I'll start with a very basic definition that how a chemist envisions energy. So basically, I would say, if I talk about the reactions, energy is everything in the chemistry. It's at the beginning of the chemistry, it starts from the energy, and if you'll go at the end, almost, I would say almost all of the chemistry you can understand, and especially the reaction mechanism you can understand in terms of the energy. So here I'm showing the reaction energy profile for one of the very fundamental reaction, where a hydrogen atom comes up, pulls up another hydrogen atom from HBr, leads to the formation of the hydrogen like H2, and the bromine atom leaves. So here the geometry of the atoms is on the x-axis, where as you are moving right, the distance between the hydrogen is shrinking, leading to the formation of the hydrogen bond, and the distance between the hydrogen and the bromine is increasing. And you can see the variation of energies, like it starts from one of the value, goes on the top of the mountain, and then it comes down to another valley. So here, the top of the valley, which is called the transition state in the language of the chemist, and the two valleys, they corresponds to my reactant and the product. And in order to take place the reaction, the reactants must need to cross this mountain, which is called the transition height, and in the language of the chemist, it is called the reaction barrier or the activation energy. So for the reaction to take place, the reactants, they must have enough energy to cross this transition state. Okay, so this is the very simple and fundamental case, but depending upon the reaction conditions, like how your reaction is progressing, what kind of products you are expecting, and what kind of reaction conditions you have, like your temperature, pressure, and whether you are using the catalysis to speed up your reaction, the profile can change from a very simple to a very complicated one, where you start from one valley, goes on the top of the mountain, which is one of the transition states. Then you land it to another valley, which is the intermediate, which is typically a very short-lived species. Then it goes to another mountain, and then finally it lands to give you the products. And in the laboratories where chemists are working for the reactions, this kind of the reaction mechanisms, they are typically encountered. And then based on these reaction energy profiles, you can actually classify your endothermic and the exothermic reactions, which all of us have read in our chemistry textbooks. So in the exothermic reactions, the energy of the product, it is less than the energy of the reactant, and this energy difference is released to the atmosphere in the form of the heat or the light. While in the other case, the opposite one, which is your endothermic reactions, the energy of the product is higher than that of the energy of the reactant. So in this case, for the reaction to take place, the reactants will absorb certain kind of the energy in form of heat or light to give the necessary product. And then there are two types of energies here. The first is, as I already told, the activation energy. So which is basically the energy required to cross the mountain, and it is the energy difference between your transition state and the reactant, and it is actually the rate determining step of the reaction. So it's like higher your activation energies and more difficult it would be for the reaction to take place. And the second one is the reaction energy, which is basically the energy difference between the reactant and the product, which will actually decides the stability of the product. So it's like lower the reaction energy, the more stable will be your product. And if I talk about the rate or the speed of the reaction, there are basically two factors. The first is the temperature. So it's like if the higher the temperature, the more easy it will be for the reaction to take place. And the second thing is the activation energy. The higher the activation energy, the more difficult it would be for the reaction to take place. And both these factors, they are considered in this Arrhenius equation, which is typically used to determine the rate of the reaction. Okay, moving on. So this is the reaction profile which is typically encountered when you have one reactant, but at the end you are expecting that that your reactant is giving you the two different products. So here you can see I have my starting material on the left hand side, and on the right hand side I have two products which are shown by the orange and green colors. So the orange one, it is having the lowest reaction energy and it is the most stable one, and its corresponding activation energy is also less. So in this case, the Bell's-Evans-Kalani's principle comes into the action, which states that there is a linear correlation between your reaction energy and the transition activation energy. So the product which has the lowest reaction energy and the lowest activation energy, this product is going to be formed in the major quantity. But this is not always the case. In some of the reactions, there are these crossing pathways in which you can see the product with the lowest reaction energy, the green one, it is not actually the one whose activation energy is also less. So in this case, like the ratio, like which of the product is going to be formed in the major quantity, it is actually decided by the two factors. First is the kinetic control and the second is the thermodynamic control. So in the kinetic control, the product ratio is determined by the rate at which the products are formed, while in the thermodynamic control, the product ratio is determined by the relative stability of the product. So here you can see, if I will talk about the kinetic stability, then in that case, my orange product is going to be formed, because in this case, the orange has the lowest transition state energy, while in the another case, if I look for the thermodynamical control, then the green one is going to be formed because it is going to be the more stable product. So it really depends upon the reaction condition, whether your reaction is going to be kinetically controlled or thermodynamically controlled. So here I would just like to talk about one of the projects which I was working in collaboration with Professor Mark Greenhalgh at University of Warwick, where we were trying to predict for this alkyl azide reaction. So there was a reaction between the alkyl and azide in the presence of the ruthenium catalyst, which leads to the formation of the two products. So what they did is they tested it with the different substituents here, like listed in the table, and for all the substituents they found that this product 3A is formed in the major quantity, while the other one is always like kind of minor. So here we wanted to understand the regioselectivity of this reaction, particularly towards the major product 3A. So I would just like to show here the pathway that we got. So I'll not go into the details of the intermediates, but I'll just tell, but because here the reaction is in the presence of the catalysis, and here all the intermediates as well as all the transition states, they are going to be in the presence of their ruthenium catalyst, which is a bit tricky to deal with the computational tools that we are using nowadays. And this is the reaction mechanisms that we got, in which if I look at the final energies of 3 and 3A prime, they are quite close. But if you look at this black one, this pathway is always having the less energy than that of the red one, which leads us to finally predict that why the 3A product is always formed in the major quantity. But then it took us around more than a month to figure out that what's happening around and what are kind of intermediates which are involved in this kind of reaction. So here automatically the question comes that can we automate the characterization of such reaction pathways, especially with the advancement in the computer technologies and the upcoming machine learning algorithms? Can we really automate the characterization of the reaction pathways, especially for such complicated reactions, and also beating the accuracy with which nowadays that human guided characterization is giving? So the answer is yes, for sure, why not? So here, if we look at the automated transition search algorithms, there are two kinds of algorithms which are available in the literature. The first one is the single-ended method, and the second one is the double-ended method. So what we do here is, in the single-ended method, the user has to just provide with the information of your reactant, and the algorithm will search automatically for all the transition states and the intermediates, and it will generate the complete reaction profile. So this one is quite good, but since you are just giving one structure and you are giving enough freedom for your algorithm to look into all the directions, so this is quite costly, and it is.
They are giving the presentation. Already started it.
Can you please mute your microphone? Okay. So this is quite costly, and it is limited to the reactants, which is consisting of only around 10 to 12 atoms. While on the other hand, in the double-ended methods, the user has to provide with the chemical information of the reactant and the product, and then it will search for all the transition states and the intermediates, and it will give you the reaction profile at the end. Here I will talk about one of the algorithm which is very widely used in the literature nowadays, that is AutoDE. So this is also a kind of double-ended method, which is open source Python program, and which can locate the transition states and intermediate. And you just provide the input structures of your reactant and the product in the terms of 1D reaction smiles. What are reactions profile? I'll just come into it. So you just provide the information about the reactant and the product, and at the end of the day, it will give you the complete reaction energy profile. And it is applicable to both organic as well as organometallic reactions, which are a bit tricky to do. So what are reaction smiles? So reaction smiles, it's a kind of a secret language which are used by the chemist or most of the people who are working in the chem informatics, where you kind of, it's like a textual representation of the molecules, where you have certain rules and regulations to represent your molecules. Like for the atoms, you use the symbols. And then if you have the bonds, like single, double, and triple bonds, they are represented by this single or double notations. And for the branching, you can use the parentheses. And similarly, you have certain rules for the aromatic and the non-aromatic rings. So this is quite a useful tool which you can use. Just feed the information, the reaction smiles of your reactant and product, and then it will give you the final reaction energy profile. This is the workflow which is used by AutoDE to generate the reaction mechanisms. So it's not only like it's looking for your reactant and the product, but it will also look for the lowest energy conformations. Like it starts, you start here with providing your reactant information, and then it will convert your smiles to the 3D structure, and then it will look for all the possible conformers and provide you the information about the reactant and the product in the form of the 3D representations, the way molecules actually look. And then it will look, okay, if your reactants and product are isomorphic, that is, they are exactly have the chemical structure, it will just stop by. But otherwise, it will proceed. It will proceed into next step, looks for the transition state database, and then eventually going through the whole cycle, it will finally give you the complete reaction profile. Here I will just give one of the examples. So it has been used for predicting the several reaction mechanism. One of the most significant example I found is this Heck-Breslow hydroformylation reaction. So this is basically a reaction in which one of the alkene, it got converted into the aldehyde in the presence of the CO2 and H2O. So this is quite a complicated reaction in which a lot of key intermediates and the transition states were involved. But with AutoDE, the authors were enabled to predict these reaction mechanisms in around 26 hours and predicting all the key intermediates and the transition states. But of course, it comes with certain limitations, which involves, first of all, this is completely based on the DFT calculations. I'll not go into the details, but if I talk about the DFT calculations, there are certain errors which are associated with the exchange and correlation functionals. And there are error bars which are of around 2 to 5 kcal per mole, which are associated with the DFT calculations. And the second most important thing is also we can automatically. Okay. So although we can automatically generate the structures of the intermediates and transition states, but what we cannot do with these automated stuff is we cannot model these solvents coming into the picture, which is actually there in almost all the reactions taking place in the laboratories. But here it's extremely difficult to take into account the effect of the solvent, which plays a very fundamental role in predicting the reaction mechanism. And the second thing is, if you have the reaction such as kind of bifurcating surface where you have one transition state and it is giving you the two products, such complicated reactions we could not do with such automated transition states, such algorithms. So all these limitations motivated us to look for the machine learning algorithms that can be combine these automated transition state search algorithms with the machine learning algorithms, so as all our limitations are taken into account. So here, the promise of the machine learning potentials is to beat the accuracy of both the traditional molecular mechanics as well as the DFT-based methods. So what we do here is, in the traditional DFT-based methods, we start with the Cartesian coordinates, provide the basis set, solve the Schrödinger wave equation, which will give you the final energy and the forces. But with the machine learning potentials, the process is a bit different. Here, you basically, instead of the basis set, you talk about the representations, which are basically the descriptors or the figures you are trying to incorporate, which are generally based on your internal coordinates or the density-based descriptors. And then you feed it to a kind of regression task, which is like you can use any kind of the machine learning models, which are available like neural networks or the kernel type approach. And then you finally end up with your energies in the forces. But the basic workflow, it includes, like, first of all, it's like encoding, and then you have to train your machine learning model and validate it, and then you apply it to the different data sets to see if it is actually working or not. So this is a general thing, but if I talk about the specifically using these algorithms for the reactions mechanisms, it's not so easy. The reason is this, because if I look for the training data sets, it's generally the thing, the bigger is your training data set, the more accurate is your model is going to be. Like if I look at the traditional ML algorithms, including the which are used for the image recognitions and so on. So here people are using like thousands or millions of data sets to train the model. But here in case of the reactions, we do not have enough data points, because as I already told, even with the automated transition search algorithms, we do not have enough data points or enough reactions, like thousands or millions of the reactions to train the model. So in this case, I think the biggest data set that I have encountered is of around 1 lakh reactions. So in this case, you have to come up with a method where you can actually control the accuracy of your system, but by also limiting the number of the data sets. So here I will just talk about one of the report that came in 2017, and then they talk about the accuracy of the machine learning algorithm using current descriptors. So they took a training data set of around 450,000 reaction entries, which was only with the reactants and products, not with the transition state, because it is extremely challenging to go for the transition state. And then they use a series of machine learning algorithms and the RDK descriptors, which are usually the constitutional or kind of structural descriptors they used. And what they come up with is this, like even if they are increasing the number of descriptors to up to 400, and using this machine learning model to predict the reaction yield and reaction times, which is a kind of binary prediction, then the error was around, it was around 65 to 75% of the error they were getting. And even if they're increasing the number of the reactions, like going to around 10 raised to power 5 reactions, even then the error was around 30%. So this is not typical for any machine learning algorithm. So this clearly calls for the need of the new fundamental reaction descriptors, which are more chemically relevant and which can then be used to predict the reaction mechanism. So talking about the type of the descriptors which are traditionally used, they're kind of constitutional descriptor, like what kind of atoms you have, what kind of bonds you have, rings you have. Then we have geometrical descriptors talking about the surface area, volume, the thermodynamical descriptors, and quantum chemical descriptors talking about the total energies and the vital energies. But out of it, the most important one is the reactivity descriptors, which is like chemical potential, hardness, softness, and electrophilicity indexes, and so on. So all these chemical concepts, they are widely used by the chemist when they're talking about the reactions. but they are not like very sharply defined definitions of such reactivity descriptors to quantify it. So in this regard, conceptual DFT comes into the picture, which provides a way to quantify these reactivity descriptors in terms of the derivatives of the energies with respect to the number of the electrons and the external potential. So where you can actually quantify various descriptors such as electronegativity, electron density, and the chemical hardness just in terms of the derivatives of the energy with respect to number of electrons and potential. Apart from these reactivity descriptors, there are certain electronic structure principles which governs the direction of the reaction. Out of all those principles, one of the principles is maximum hardness principle, which states that there seems to be a rule of nature that molecules arrange themselves to be as hard as possible, which means if we are going from the reactant to the products will always have a tendency to be hard, to be more harder than that of the reactant. So here we just try to look into the different data sets that whether they actually satisfy these maximum hardness principle or not. So these are the results. So here what we got is out of around 50 to 100 reactions we encountered, it was based on the different definitions of the hardness, it was around 80% of the reactions, they were actually satisfying this maximum hardness principle, which gives us more freedom to use such kind of the data sets and combine it with the machine learning algorithm. Okay, so wrapping up, currently I have validated the electronic structure principles for the wide range of the data sets. And now I am generating the data sets, such transition states data sets with AutoDE, but accompanied by the calculation of the quantum chemical reactivity descriptors, and which I'll be further using for training the machine learning model with the ARD strategy and inverse molecular design principles, which I'll be doing at the University of Warwick by the end of this year. Thank you.
Thank you, Ashima, for this nice talk. Is there any questions? Okay, I will do one myself for like big curiosity. How are you generating the smiles? Are you doing it like yourself, or you will use some...
There are several softwares which are available, which can, if you have the chemical structure, and then you can use those softwares to convert into the reaction smiles, or do it vice versa. Like if you have reaction smiles, then you can just load into that software, and it will give you the complete molecular structure of the system.
Okay, and you can couple those with other programs that you are using for the machine.
Yes,
or...
I think I'm not sure about I'm not sure about the Camera, but I think there are like Chemexon and Marvin, which you can use to convert these reaction smiles into a structure and vice versa things.
Someone else? Okay, if not, we can come to the third speaker of today. Okay, our last speaker of today is Hanh Tran from the second cohort. She obtained her PhD degree in industrial biotechnology in Thailand at the University of Prince Songkhla in in 2009. She obtained his master's in mycology at the University of Kaesar in Thailand, and her bachelor in biology also in Vietnam in 2003. And prior to her PhD completion, she was a lecturer at the Faculty of Environmental Management at Prince Songkhla University. And then she moved back to her home country and started working for International University in 2010. She has published 18 peer-reviewed articles, 2 book chapters, and a book on slime mold, and has been an associate editor on Slime Molds Journal and another well-known journal in her topic. And today she will talk about physiochemical characteristics and neuroprotective effects of melanins, derivative from Calvatria cranformis and Shiraria species. So the floor is yours.
So it should be open, yeah. You can see the screen share, which is strange because here it's share a screen. Yeah, I'm just going to take the presenter view out then, because yeah, now it's correct. Okay, so just with the arrow keys.
Thank you. Thank you. So today I will introduce some initial results of my research about the neuroprotective effects of melanins and modified melanins from some selected fungal species. So first of all, neurotoxins. Neurotoxins are linked to several neurodegenerative diseases like Parkinson's. Neurotoxins like hydrogen peroxide can be generated inside our bodies, and normally with the small amounts it would be okay because of our bodies have the mechanisms to break it down or to get rid of it. But due to some reason, if this kind of toxin is accumulated with high amounts, and then it would destroy or ruin or mess up the neuronal cells. Besides the internal neurotoxins, neurotoxin can come from external environment like MPTP, and in terms of Parkinson disease, currently there are more than 10 million people suffering from this worldwide. Next, I would like to explain why I'm interested in melanins, fungal melanins and modified melanins. So melanins is produced by a number of organisms, including humans. And regardless of the origins, melanins have numerous or broad spectrum of biological activities, including antioxidant and some other activities. So the thing about melanins is that even though they are very potential, but the actual application of them is challenging because they are mostly not soluble in water. And also some other common solvents. They are, however, soluble in alkali solution. Luckily, previous research suggested that when you modify melanin with some amino acids, you can enhance the solubility, their solubilities, and then subsequently can enhance some of their biological activities. That's why in this research, besides the original melanins, we also are interested in amino acid modified melanins. And why we are interested in this kind of fungal species? We will work with a number of fungal species, but I am presenting here two of those for two reasons. First of all, this kind of fungi produce either black or brown fruiting bodies, which indicates the presence of melanins. And also the second reason, which is more practical, is that they produce a large amount of sample. So if they are potential, and then we can scale the production of melanin afterward. So here's the research objective. So we extract and modify melanins from these fungal species, and then we evaluate their abilities to protect neuronal cells from some toxins like hydrogen peroxide and MPTP. This is the research flowchart. So maybe I should go back. We extract the black and brown pigments, and then we characterize the pigments to see if they are actual melanins or not. And then we modify the melanins, and then we test for the cell protection activities. So after we extracted the black or the brown pigments from those fungal species, we have to screen for the indicated characteristics of melanins. Some of those is that melanins have a strong absorbance toward UV light, which means in the wavelength of from 200 to 4 or something. And then they do not absorb normal light, meaning at a longer wavelength light. That is one of the simple or indicators. And the second indicators is that when you do the FTIR scanning, some of, if they are melanins, they have some indicated peaks, like those in these regions. And also beside melanins, the blue lines here, we also scan with the modified melanins, and you can see one additional peak in the modified melanins, which indicate the amino acids arginine has been attached to the molecules. However, we didn't know exactly what happens when we mix the two things together. It's quite random, and later we would try to figure out what exactly happens and why the solubilities can be enhanced. So the original melanins are insoluble in water, but the arginine modified forms of them are soluble in water. Next, this is a bit messy, but if you are patient, I will explain you here. So we culture the neuroblastoma cells, neuronal-like cells, and then we introduce the toxin, in this case, which is a hydrogen peroxide. And then we also have some treatments, treated the mixture of neuronal cells with the toxins and with different concentrations of the samples, meaning either melanins or modified melanins of the two fungal species. And we also have a positive treatment, which includes the toxins and also the commercial drugs, resveratrol or something, with this concentration. So I will go into the detail here. The first column is the cells under the normal condition. The second column is the cells treated with the toxin or hydrogen peroxide alone. And the next one is the cells treated with the toxin and the drug, commercial drug. And this is the cells with the toxins and with the samples at different concentration. So the red color here is the melanin of the buffalo or craniformis. In the orange is the modified form of it. In the green one here is of Filaria melanin. In the olive color here is of the modified melanin of Filaria. And this is at 10 microgram per ml, and this at 20, 50 to 100. And you can compare, you can see like especially at high concentration, like 100 milligram per ml, both of the samples can protect the cells from the hydrogen peroxide because of the cell viability from these treatments are significantly higher than the treatment without the toxins. And similarly, we treated the cells, we replace the hydrogen peroxide with MPTP. And then for this case, only the sample of Filaria, both two forms, can protect the cell effectively from the toxins. It should be noted that the positive control didn't work well in this case. So the ability to protect cells from this hydrogen peroxide and MPTP depends on each fungal species, the nature of each fungal species, and also it depends on the forms. Like sometimes when you modify the melanins, but the activity may not be enhanced. But in this case, it is enhanced with the Filaria samples. That's all for my talk. Thank you for listening.
Thank you, Han. Is there any questions?
Yeah, I have a question. So the peroxide and the MPT, I mean, those are both toxic, but they work very differently because there's a against peroxide, but not that much against MPT, right?
Right.
So the melanin protects against peroxide and how exactly does it protect peroxide? Is it just like taking in the clinical
At this point, we haven't investigated the mechanisms yet. However, so first of all, I agree, because the toxicity is caused by hydrogen peroxide and MPTP is different. And now, for hydrogen peroxide, for MPTP, it would be it can cause some kind of more permanent or more severe damages compared to hydrogen peroxide. I guess, get back to the question, I think maybe the ability to protect cells from hydrogen peroxide more effectively has something to do with the antioxidant or scavenging ability of melanins. But I don't know the exact mechanisms yet.
And it also protects against the other. It would be interesting to know how it works because it seems like doing something.
This step where we just are screening for potential sample, and then we would go a little bit more further into the mechanisms. Yeah.
Okay, thank you.
Thank you. Yeah.
Are there any more questions? I have a curiosity. How easy or difficult is to find those species here, or like in Belgium, or do you need to go somewhere else to find it? Or?
some melanin producing mushrooms can be found in Belgium, but I've collected them from all over the world. Like some I collected by myself, and some others collected and sent them to me.
Like a collaboration with other groups, or
Some I'm not actually scientists. They are just my friends, and then they went out for a walk and they saw some buffalo, because I constantly remind them like I need this kind of sample. So sometimes they took a walk and they saw some mushrooms and they asked me, "Do you want me to go back there to get the mushroom for you?" And I said yes, and they did. Oh, yes, actually.
that's great. I would like to remind you to fill the online form, and I would like to thank all the speakers of today.
Right, so I don't know if anybody wants to say anything else more generally from the SIF perspective. Maysan, do you have any messages from Thibault?
Excuse me?
Do you have anything that we need to tell the fellows from the program?
No, there's any message or no, thank you.
All right.
I created the breakout rooms. Should I open them?
Yeah, I think so. There's quite a lot of people who are participating online. They can go to the breakout rooms and we can just have a breakout room here in the room with the people who are present to chat. Does that make sense? Or did you normally send the speakers to the breakout rooms?
If there's people online, I can just open the breakout rooms for them. And yeah, I think I do. I will do.
Do you want to join them?
Yes, I can join the.
Oh, sorry, no,
breakout
I'm
rooms.
asking the speakers that are here what they want to do.
Yes, there's one breakout rooms for each speakers.
Okay, so you guys, they can. Okay, do you want to go check in on your breakout room then, each of you? Maybe.
If people have questions, I can just open the breakout rooms. Just tell me if it's necessary or not for me to open.
I think it's up to the crowd then. The
Okay.
people present. Do you want them or not? Tell Maysan, please. I think we can stop recording.
I will just open them. If you have any questions, you can go to the breakout rooms.
Okay, great. All right, everybody, thank you. Yeah, I mean, you guys can